Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. There is a place you return to when the world becomes too loud. A rooftop, perhaps, or a hillside where grass bends under evening wind. The night is quiet here. Not silent, silence is absence, and the night is full, but quiet in the way old things are quiet. Patient, waiting. You lie back. The sky opens above you like a vast, inverted ocean. Stars flicker at distances your mind cannot quite hold. And there, hanging in that infinite dark, suspended as if by invisible threads, is the moon. You have seen this face before. 1,000 times. 10,000. Every clear night of your life, the moon has worn this same expression. Craters clustered near what we call the Sea of Tranquility. Dark plains that ancient observers thought were oceans. Bright rays spreading from younger impacts like frozen fireworks. The features shift slightly with the passing months, the angle of light changes, shadows grow and shrink, but the face itself remains. Always the same face. You might not have noticed this constancy until someone pointed it out. But once you know, you cannot unknow. The moon never turns away. It never shows us its back. For all of human history, for every eye that has ever looked up from this planet, the moon has presented one hemisphere, one eternal portrait, while hiding the other in perpetual mystery. This is strange. Everything else in the heavens seems to spin. Earth rotates, giving us day and night in a rhythm so fundamental we measure our lives by it. The sun spins, though it takes a month to complete one rotation. Mars spins. Jupiter spins so fast it bulges at its equator. Even distant galaxies spiral in vast, patient turns across billions of years. Spinning is what things do. It is the default state of matter in motion. When clouds of gas collapse to form stars, they spin. When planets coalesce from dust, they inherit that rotation. Angular momentum is conserved, transferred, but rarely lost. The universe spins. So why does the moon appear frozen? The answer is not simple. It is not something you can explain in a single sentence, though you might try. Tidal locking, you could say, and technically you would be correct. But those words are just labels, containers for a deeper truth. To truly understand why the moon shows us only one face, we must travel back through billions of years. We must watch gravity do its slow, patient work. We must see how energy changes form, how motion becomes heat, how chaos settles into the stillness of equilibrium. This is a story about time. About forces too subtle to feel but powerful enough to move worlds. About the way everything in the universe eventually finds its place of rest, or at least, its place of least resistance. The moon does spin. That is the secret we will uncover together. It spins exactly once during each orbit around Earth, a perfect synchronization that makes it appear motionless from our perspective. This is not coincidence. This is not magic. This is physics doing what physics always does, finding balance, minimizing energy, settling into patterns that can last for eons. But how? And more importantly, why? The night deepens around you. The moon hangs there, patient as always, holding its secrets. But tonight, as you stare up at that familiar face, you begin to sense the motion hidden within the stillness. You begin to understand that what looks like frozen time is actually the slowest dance in the solar system. A waltz between worlds that has been going on since before there were eyes to witness it. The answer lies in gravity, in tides, in the friction between moving things. It lies in the deep past when Earth and Moon were young and wild, when days were shorter and the moon hung so close you might have thought you could touch it. It lies in the slow transfer of energy, the patient work of forces that never sleep. The moon does not refuse to turn. It has simply found its rhythm. And in that rhythm, we can read the story of how all things in orbit eventually find peace. Let us begin. From where you stand, the moon appears locked in place. Not in position, you can watch it rise and set. Track its path across the night. See how it wanders through the constellations on its monthly journey. But in orientation, in the direction it faces, it seems utterly still. The same patterns of light and shadow. The same craters marking the same locations. A cosmic portrait that never changes its pose. This is the illusion. Not a deception, exactly. But a perspective trick. What you are seeing is real. But the interpretation that the moon does not rotate is incomplete. The moon does rotate. It turns on its axis just as Earth does. Just as most solid objects in space do. But its rotation has become synchronized with its orbit. In such a perfect way that from Earth, we cannot perceive the turning. Imagine you are standing in the center of a room. In your hand, you hold a ribbon. And at the ribbon's end, someone walks in a circle around you. If that person wants to keep facing you as they circle, they must turn. They must rotate their body to match their movement around you. One complete trip around the room requires one complete rotation of their body. From your perspective in the center, they never turn away. You always see their face. But from the perspective of the walls, they are clearly spinning. This is what the moon does. As it travels around Earth, a journey that takes roughly 27 days, it also rotates on its axis. One orbit, one rotation. The timing is exact, synchronized to the smallest fraction. This is why the same hemisphere always faces us. Not because the moon is still, but because its two motions, revolution around Earth and rotation on its axis, are perfectly matched. We call this tidal locking, though the term barely hints at the elegant mechanism behind it. It is a state of equilibrium, a configuration where the moon's rotational period exactly matches its orbital period. From our viewpoint on Earth's surface, this creates the appearance of a moon that never turns. But step outside our perspective, watch from the distant stars, and you would see clearly. The moon spins, slowly, patiently, once per orbit. This perfect synchronization feels purposeful, as if the moon were deliberately showing us one face, while hiding the other. Ancient peoples wove stories around this mystery. They imagined the far side held secrets, perhaps a different landscape entirely, or a realm where the rules of our world did not apply. Even in the modern era, before spacecraft circled the moon and sent back images, the hidden hemisphere captured our imagination. What lay on the other side of that cosmic coin? The answer, when we finally saw it, was both surprising and somehow fitting. The far side looked similar to the near side, cratered, ancient, marked by the same violence of the early solar system. But there are differences. Fewer of the dark plains we call Maria, a thicker crust, a terrain that, while not alien, is distinctly its own. For 4 billion years, this landscape faced the stars, while we went about our lives, never seeing it, never knowing what features marked its surface. But we are getting ahead of ourselves. The question is not what the far side looks like, but why there is a far side at all in our experience. Why does one hemisphere remain forever hidden? Why this perfect lock between rotation and revolution? The answer requires us to travel backward in time, to an era when Earth and Moon were not the calm, stable pair we know today. Back then, things were different, violent, young. The moon spun faster, Earth spun faster, and the distance between them was a fraction of what it is now. The tidal lock we observe today was not a feature of the moon's birth. It was something that developed gradually, over millions and millions of years, through a process so subtle you could never watch it happen, but so inexorable that nothing could prevent it. To understand this process, we need to understand tides. Not just the rising and falling of ocean water, though that is part of it, but the deeper, more fundamental way that gravity shapes and stresses and gradually reshapes everything it touches. Tides are not gentle. They are gravity's patient violence, working on scales too large and too slow for human perception, but powerful enough to move worlds. The moon appears still, because it has given up the last of its independent rotation. Gravity has done its work. Over eons of time, the bulging and flexing of tides drained away the moon's rotational energy, degree by degree, until what remained was this: a perfect match, a synchronized spin, a face that always looks homeward. This was not sudden. There was no moment when the moon clicked into place and stopped turning. The process was gradual, asymptotic, approaching perfection across timescales that dwarf human civilization. And the same process is still happening now, slowly, to Earth itself. But we are speaking too quickly. First, we need to go back to the beginning, back to a time when the moon was not a quiet companion, but a violent neighbor, back to when Earth and Moon first met, and the dance that would shape both of them for billions of years was just beginning. 4.5 billion years ago, There was no gentle moonrise. There was no calendar measuring 28-day cycles. There was only chaos, heat, and the aftermath of collision. The moon was born from violence. The prevailing theory suggests that a Mars-sized body, which we call Theia, struck the young Earth in a glancing blow. The impact was unimaginable in its energy, enough to vaporize rock, to throw immense quantities of debris into orbit, to reshape both bodies entirely. From that ring of molten material, from that vast cloud of Earth stuff flung into space, the moon gradually coalesced. It gathered itself from the wreckage, particle by particle, molten droplet by molten droplet, until a new world hung in Earth's sky. But this moon was nothing like the one we know. It was close, astonishingly close. Where today the moon orbits at a comfortable distance of roughly 384,000 kilometers, the young moon may have been only 25,000 kilometers away. Perhaps even closer. In the sky, it would have appeared enormous. A vast sphere filling perhaps 10 or 15 degrees of arc. If you could have stood on Earth's surface then, if there had been a solid surface to stand on, if the planet was not still partially molten from the impact, the moon would have dominated the heavens. An impossibly large presence, close enough that you could see features in detail without any aid, close enough that its gravitational influence was overwhelming. Earth was different too. It spun far faster than it does today. A day lasted perhaps only 5 or 6 hours. The planet whirled through space, rotating so rapidly that it bulged noticeably at the equator. This was a world in a hurry, young and energetic, not yet slowed by the patient drag of tides. And the moon? The moon spun too, but not in synchrony with its orbit. We do not know exactly how fast the early moon rotated. That information is lost to time, but it was almost certainly faster than its current rate. The moon had its own rhythm then, independent of Earth. As it orbited this nearby, rapidly spinning planet, different faces would have turned toward Earth. The features we know, the seas and craters of the near side, would have rotated in and out of view. The moon had not yet been tamed. The gravitational relationship between these two bodies was intense. Imagine the tides on Earth, with its forming oceans and still molten rock. The moon's gravity would have raised immense bulges. Water and stone would have heaped upward, pulled toward the moon as it passed overhead. On the moon, though it had no oceans, Earth's much stronger gravity would have created even more dramatic deformations. The moon's interior, still partially molten from its formation, would have bulged toward Earth, creating tide after tide after tide. These were not the gentle oceanic tides we experience today, rising and falling by a few meters. These were tides measured in tens of meters, perhaps hundreds. The ground itself would have risen and fallen. The rock would have flexed. And with each flexing, with each rise and fall of these gravitational bulges, energy was transformed. This is the crucial point, the seed from which everything else grows. The tides were not passive. They did not simply rise and fall without consequence. The motion of these bulges, the flexing of material, created friction, internal friction, as layers of rock or molten material moved against each other. And friction converts motion into heat. Think of rubbing your hands together on a cold day. The mechanical motion of skin against skin becomes warmth. Energy of one form, kinetic energy, the energy of motion, becomes energy of another form, thermal energy, heat. This transformation is everywhere in physics. It is how brakes slow a car, how a meteor burns in the atmosphere, how any moving thing gradually loses its motion to the universe around it. The young moon, bulging toward Earth with each orbit, flexing and deforming as it spun, was converting rotational energy into heat. And Earth, with its massive tides raised by the nearby moon, was doing the same. Both bodies were losing energy through this tidal friction, though in different ways and at different rates. For Earth, the tides worked to slow its rotation. The moon's gravity pulled on the tidal bulge, creating a torque, a twisting force that acted like a brake on Earth's spin. Days lengthened. Imperceptibly at first, you could not measure the change in a human lifetime or 1,000 lifetimes. But relentlessly, over millions of years, Earth's rotation slowed. The 5-hour day became 6 hours, then 8, then 12. Gradually approaching the 24-hour day we know. For the moon, the process was different but related. The moon was smaller. Its tides were raised by Earth's stronger gravity, and the tidal forces acting on it were more intense relative to its size. The moon's rotation was being braked more quickly than Earth's. And because angular momentum must be conserved in the system, because the total amount of spin cannot simply disappear. As the moon's rotation slowed, something else had to change. The moon began to drift away from Earth, gaining orbital angular momentum to compensate for the rotational angular momentum it was losing. This might seem paradoxical. How can slowing down make something move farther away? But in orbital mechanics, objects at higher orbits move more slowly in their paths around the central body. The moon was not moving away because it was speeding up in its orbit, but because angular momentum was being redistributed. As tidal friction drained rotational energy from the moon, the same forces pushed it into a higher, more distant orbit. So the early Earth-Moon system was dynamic, changing, unstable in a slow-motion sense. The moon spun down, orbit by orbit, tide by tide. Earth spun down too, though more slowly. And the distance between them grew, centimeter by centimeter, year after year after year. This was not a quick process. The timescales involved are difficult for human minds to grasp. We think in days, years, maybe generations if we try. But the moon's transformation from a fast-spinning, nearby body to a tidally locked, distant companion took hundreds of millions of years, perhaps a billion, time enough for continents to form, for oceans to cool, for life to begin and diversify and spread across the planet. And through all of that time, through all those eons, the tides never stopped their work. They flexed the moon with every orbit, slowed its rotation degree by patient degree, until finally, though there was no moment we could point to and say here, now, this is when it happened, the moon's rotation period matched its orbital period, one face locked toward Earth, the other facing forever outward. This was tidal locking, not an event, but a destination. A state of equilibrium that, once reached, was stable. The moon could no longer easily change its rotation rate relative to its orbit, because the tides that had slowed it now worked to keep it synchronized. Any deviation from perfect locking would create new tidal bulges, new friction, new forces that pushed the rotation back towards synchrony. The wild moon had been tamed, but the question remains, how exactly did this happen? What is the mechanism that turns a freely spinning world into one that shows only a single face? To answer that, we need to understand tidal forces more deeply. We need to see how gravity reaches across the void and reshapes everything it touches. Gravity is patient. It does not demand. It does not push or shove or insist. It simply pulls, gently, constantly, on everything that has mass. And because it never stops, because it never tires or falters, it can accomplish things that no amount of sudden force could achieve. When we think of gravity, we often imagine it as a single force between two objects. Earth pulls on you with a certain strength. You pull back on Earth with exactly the same force. Though Earth is so massive that your pull has no measurable effect. This is Newton's elegant insight. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. But this is a simplification. Gravity does not act on objects as single points. It acts on every particle, every atom, every bit of mass individually. And when an object is large enough, when it has significant size, the gravity acting on its near side is slightly stronger than the gravity acting on its far side. This difference, small but measurable, is what we call a tidal force. Imagine the moon orbiting Earth. The side of the moon facing Earth is closer to our planet than the moon's center, and therefore experiences a slightly stronger gravitational pull. The far side is farther away and experiences a slightly weaker pull. If the moon were a rigid, solid sphere, if it could not deform at all, this difference would not matter much. The moon would orbit as a whole, and the varying strength of gravity across its diameter would simply be a mathematical detail. But the moon is not perfectly rigid. Nothing is. Every object has some elasticity, some ability to deform under stress. Rock can flex if the forces are large enough and sustained enough. Even steel can bend. And when the moon feels Earth's gravity pulling harder on its near side than its far side, it responds the only way it can. It stretches. Not much. The deformation is subtle, measured in meters or tens of meters across the moon's 3,474-kilometer diameter. But it is real. The moon develops a bulge pointing toward Earth, and another bulge pointing away. These are tidal bulges, regions where the moon's material has been pulled slightly outward by the differential force of Earth's gravity. The bulge pointing toward Earth makes intuitive sense. That side is being pulled harder, so it stretches toward the source of the pull. But why a bulge on the far side? This seems counterintuitive at first. The answer lies in the fact that tidal forces are differential. They arise from the difference in gravity across an object. The far side is pulled less strongly than the moon's center. So in the reference frame of the moon as a whole, that far side effectively experiences an outward force. It gets left behind, so to speak, creating a second bulge opposite the first. Picture the moon not as a solid sphere, but as a slightly elongated shape, stretched along the line connecting it to Earth. An egg, perhaps, with its long axis pointing always toward our planet. This is the tidal deformation, the fundamental shape change that gravity creates. Earth experiences the same thing from the moon's gravity. The water of our oceans is easier to deform than rock, so the tidal bulges are more noticeable here. When the moon is overhead, the ocean beneath it bulges upward, high tide. On the opposite side of Earth, the ocean bulges again, another high tide. Between these two high tides, at the points 90 degrees away from the moon's direction, the water level is lower, low tide. We experience this as the familiar rhythm of the tides, the twice daily rising and falling of sea level. But this is only the most visible part of a deeper phenomenon. Earth's solid body deforms too, rising and falling by perhaps 30 centimeters. As tides in the rock itself flex the planet, we do not notice this, because we flex with it. There is no ocean to mark the difference. But the deformation is real, measurable with sensitive instruments. Now here is where the story becomes interesting. These tidal bulges want to point toward the source of gravity, toward Earth for the moon's bulges, toward the moon for Earth's bulges. But if the object that is bulging also rotates, the bulges cannot keep up perfectly. There is a lag, a slight displacement caused by the time it takes for material to respond to the changing direction of the tidal force. Imagine Earth rotating beneath the moon. The moon's gravity tries to pull Earth's oceans into a bulge directly beneath it. But Earth is spinning, and the water has momentum, and friction with the seabed resists instantaneous movement. By the time the water has bulged toward where the moon is, Earth has rotated slightly, and the moon has moved in its orbit. The bulge ends up slightly ahead of the moon's current position. This slight offset is crucial. Now the tidal bulge is not pointing exactly at the moon. It is pointing slightly ahead of the moon, in the direction of Earth's rotation. And because mass attracts mass, this displaced bulge pulls on the moon with its own gravity. The pull is small. The bulge is a tiny fraction of Earth's total mass. But it is enough. It pulls on the moon in the direction of Earth's rotation, slightly speeding the moon in its orbit. This transfers angular momentum from Earth's rotation to the moon's orbital motion. The result: Earth's rotation slows down, days get longer, and the moon, gaining angular momentum, moves to a higher orbit. It drifts away from Earth at roughly 3.8 centimeters per year, a rate we can now measure with laser reflectors left on the lunar surface by Apollo astronauts. For the Moon's own rotation, the process was similar, but more direct. When the Moon spun faster than it orbited, when its rotation period was shorter than its orbital period, the tidal bulge raised by Earth's gravity could not keep up with the Moon's rotation. The bulge would form. Then the Moon would rotate, carrying the bulge away from the Earth-Moon line. Earth's gravity would pull on this displaced bulge, creating a torque that acted to slow the Moon's rotation, orbit after orbit. This torque worked against the Moon's spin. The Moon turned a little slower. The bulges could align a little more closely with Earth's direction. But as long as the Moon spun faster than it orbited, the process continued. Slow the spin. Slow the spin. Slow the spin. Patiently. Inexorably. This is tidal friction. Though friction is perhaps a misleading word, it is not like the friction between two solid surfaces rubbing together. It is the resistance to deformation, the lag between force and response, the conversion of motion into heat through the flexing of materials. Every time the Moon flexed, every time its shape deformed slightly and then relaxed, a tiny amount of energy was converted from kinetic energy, the energy of rotation, into thermal energy. Heat dissipated into space. Where did this energy go? Into the Moon's interior, warming it slightly, into the rock and dust, and whatever molten materials still existed deep within. And from there, radiated away into space as infrared light. The energy did not disappear. Energy never disappears. But it changed form. It went from useful, organized motion to useless, dispersed heat. The Moon's rotation slowed, and the universe grew imperceptibly warmer. The tidal forces did not care that this was happening. They are not conscious, not purposeful. They simply exist, a consequence of gravity acting over distance. But the effect was as certain as mathematics. The Moon's spin slowed, 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 until it matched the orbital period. Once per orbit, the same face turning toward Earth. Equilibrium. And once that equilibrium was reached, it became stable. Any rotation faster than the orbital period would create a displaced tidal bulge, which would slow the rotation. Any rotation slower would create a displacement in the opposite direction, which would speed it up. The locked state was a minimum energy configuration, a valley in the landscape of possibilities. The Moon had found its rest. This is how the invisible hand of gravity shapes worlds, not through sudden events or dramatic transformations, but through the patient accumulation of small effects. Tides rise and fall. Rock flexes and heats. Rotation slows. And over time, geological time, deep time, time measured not in human generations, but in the ages of continents, everything finds its balance. The Moon stopped turning. from our perspective. But really, it found a different way to turn. A synchronized way. A way that looks like stillness, but is actually the slowest, most patient rotation imaginable. And the mechanism behind all of this? Friction, energy loss, the gradual conversion of motion into heat, and heat into the cold void of space. There is a principle in physics, simple enough to state, but profound in its implications. Energy cannot be created or destroyed, only converted from one form to another. This is conservation of energy, one of the deepest truths we know about the universe. Every transformation, every motion, every change follows this rule. The energy before must equal the energy after. Nothing is gained. Nothing is lost. Only changed. But there is another principle. Related, but different. That tells us about the direction of change. It tells us that energy, while never destroyed, can become less useful. It can spread out. It can transform from concentrated, organized forms into dispersed, random forms. This is entropy, the measure of disorder, the arrow of time built into the structure of reality itself. When the moon spins, it possesses rotational energy. This is kinetic energy, energy of motion, organized and directional. Every particle in the moon is moving in a coordinated way, rotating together around the moon's axis. This is low entropy, high organization, high usefulness. When tidal forces flex the moon, when rock deforms and then relaxes, some of that organized rotational energy becomes heat. Heat is still energy, but it is energy in a different form. It is the random motion of atoms and molecules, vibrating and jostling without coordination. This is high entropy, low organization, low usefulness. The transition is irreversible. Once rotational energy becomes heat, it does not spontaneously become organized rotation again. The heat disperses, radiates away into space, and is lost to the moon forever. The moon spins a little slower. The universe is a little warmer. And time has moved forward. Entropy has increased, as it must always increase. This is tidal friction in its deepest sense. It is not friction like the rubbing of hands, though that is a useful analogy. It is the fundamental conversion of organized energy into disorganized energy. It is the universe doing what the universe always does, moving from order toward disorder, from concentrated energy toward dispersed energy, from high organization toward equilibrium. For the young moon, spinning rapidly while orbiting Earth, this meant a slow drain of rotational energy. With each orbit, tidal bulges formed and dissolved. With each flexing, rock heated slightly. With each heating, energy radiated away. The moon's rotation slowed, not because something was physically breaking it. There is no friction wheel, no mechanism in any mechanical sense, but because the organized motion of rotation was being converted, bit by bit, into the disorganized motion of heat. The same process affected Earth, though more slowly. Earth is more massive, so it has more rotational energy to lose. Earth's day lengthened from perhaps 5 hours to 24 over billions of years, and the process is not yet complete. Even now, tidal friction continues to slow Earth's rotation. The day is getting longer by about 1.7 milliseconds per century. This seems negligible, and in human terms, it is. But over millions of years, it adds up. Over billions of years, it reshapes everything. Where does this energy go? Into the tides themselves, heating the water and rock that flex under the moon's gravity. Into the Earth's interior, where tidal heating contributes a tiny fraction to the planet's internal warmth. And ultimately, into space, as infrared radiation that Earth emits constantly into the cold dark. The moon is also slowly drifting away from Earth, because angular momentum must be conserved. As Earth's rotation slows, losing rotational angular momentum, the moon gains orbital angular momentum and moves to a higher orbit. The 3.8 centimeters per year that the moon recedes is a direct consequence of tidal friction slowing Earth's rotation. The energy and momentum do not disappear. They are redistributed within the Earth-Moon system, following the strict accounting rules of physics. But here's the crucial insight. While angular momentum is conserved, energy is not conserved in the same way. Total energy is conserved. Yes, nothing is created or destroyed, but useful energy, mechanical energy, energy that can do work, is being lost to heat with every passing moment. The Earth-Moon system has less rotational energy today than it did 1 billion years ago. That energy did not vanish. It became heat, then radiation, then it left the system entirely. This is entropy at work. The Earth-Moon system is moving toward a lower energy state, a more stable configuration. And the endpoint of this process, the final state toward which everything is heading, is double tidal locking. Right now, the moon is locked to Earth. It shows one face, rotates once per orbit, has settled into its equilibrium state. But Earth is not yet locked to the moon. Earth still rotates faster than the moon orbits, which means tidal friction is still slowing Earth's rotation. One day, many billions of years from now, long after the sun has evolved into a red giant, and the question may be moot, Earth's rotation will slow to match the moon's orbital period. At that point, one side of Earth will always face the moon. One hemisphere will see the moon hanging motionless in the sky. The other hemisphere will never see it at all. This is the future equilibrium. Moon locked to Earth. Earth locked to moon. Both objects showing the same face to each other. For eternity, the orbital period will be much longer than it is now. Perhaps 50 or 60 present-day Earth days. the moon will be farther away, a smaller disk in the sky, and the system will be stable. Finally, in a way it has never been before. At that point, tidal friction will effectively cease. There will still be tides. The sun will raise tides on both Earth and Moon. But the Earth-Moon tidal interaction will have reached its minimum energy state. No more energy to lose to friction. No more rotation to slow. Just two worlds orbiting their common center of mass, forever facing each other, locked in a gravitational embrace that nothing short of an external disruption could break. This is where entropy leads, not to chaos or disorder in the everyday sense, but to equilibrium, to the state of lowest available energy, to stillness. The moon reached this state long ago. Its rotation slowed and slowed until it matched its orbit. And then the slowing effectively stopped. The moon found its rest. It is not motionless. It still rotates, once per orbit, but it has found the only rotation rate that is stable under the pull of Earth's gravity. And in this, there is a strange beauty. The moon does not fight against entropy. It cannot. Nothing can. Instead, it has settled into the configuration that entropy allows. It has found the rhythm that minimizes energy loss, that creates the least internal friction, that lets it exist in the gentlest possible relationship with the force that shapes it. Tidal locking is not a cage. It is a solution, an answer to the question, how can a moon orbit a planet while losing the least energy? And the answer is, by matching its rotation to its orbit, by showing one face, by moving in synchrony with the very force that would otherwise tear it apart. The moon has taught itself this solution, taught itself through the slow, automatic calculus of physics. No intelligence required, no intention, just gravity, time, and the patient conversion of motion into heat, of energy into entropy, of chaos into the deepest possible order. There are agreements in the universe that require no words, no negotiation, no conscious choice. They are agreements written into the mathematics of motion and mass. They emerge from the nature of reality itself, from the way forces interact and energy flows. Tidal locking is one such agreement. It is a handshake between two bodies, a mutual arrangement where both participants settle into a configuration that neither can easily leave. For the moon and Earth, this handshake was not instantaneous. It took hundreds of millions of years to complete, but once established, it became the defining feature of their relationship. The mechanics are clear enough now. The moon, subjected to Earth's tidal forces, experienced friction as it rotated. That friction slowed its rotation until the rotational period matched the orbital period. One face locked toward Earth, one rotation per orbit, the same hemisphere eternally visible. From our perspective, But let us think about what this means. In a deeper sense, the moon did not simply stop rotating. It found a rotation rate that is sustainable, that creates no net torque, that requires no further energy loss to maintain. This is equilibrium, but not the equilibrium of rest. It is dynamic equilibrium, the equilibrium of a system that is still moving, but moving in such a way that nothing changes. Consider the tidal bulges again. When the moon was spinning faster than it orbited, those bulges were dragged ahead by the moon's rotation, and Earth's gravity pulled on them to slow the spin. But when the rotation period equals the orbital period, the bulges stay aligned with the Earth-Moon line. There is no lag, no displacement, no torque trying to change the rotation rate. The moon turns at exactly the speed that keeps its elongated shape pointed toward Earth. This is the locked state, not locked in the sense of being prevented from rotating, but locked in the sense of rotating at a rate that is gravitationally stable. Any deviation from this rate would create forces that push the rotation back towards synchrony. The system has found a valley in the energy landscape and settled there. From Earth, this creates the phenomenon we observe, a moon that shows the same face, but from the moon's surface. The experience would be quite different. If you stood on the near side, Earth would hang in the sky, motionless. It would not rise or set. It would simply be there, in the same position, day after lunar day. The stars would wheel overhead. The sun would rise and set during the moon's long day, which lasts about 29.5 Earth days. But Earth would remain fixed, a blue marble suspended in black, waxing and waning through its phases, but never moving from its place. In the lunar sky, on the far side, you would never see Earth at all. It would be perpetually below the horizon, hidden by the bulk of the moon itself. The only celestial objects would be the stars and sun, an Earthless sky, a perspective unique in the solar system. This asymmetry has shaped the moon's geology in subtle ways. The near side, always facing Earth, and always experiencing Earth's stronger gravitational pull, has thinner crust and more of the dark volcanic plains, called Maria. The far side has thicker crust and fewer Maria. These differences are small, but measurable, a testament to the long-term effects of tidal forces. But tidal locking is not unique to the moon. It is a common outcome. Whenever a large body orbits close enough to another massive body, the moons of Jupiter are nearly all tidally locked to their planet. Io, Europa, Ganymede, Callisto, all show one face to Jupiter, just as our moon shows one face to Earth. The same is true for Saturn's major moons, Titan, Enceladus, Mimas, and others. These are not coincidences. These are solutions to the same problem: how to orbit without losing too much energy to tidal friction. Even some exoplanets are tidally locked to their stars. Hot Jupiters, gas giants that orbit very close to their suns, have likely had their rotations synchronized. One hemisphere bakes under constant starlight. The other freezes in eternal night. The temperature difference drives massive winds, weather systems that dwarf anything in our solar system. These are extreme cases, but they follow the same rules as the Earth-Moon system. Gravity creates tides. Tides create friction. Friction slows rotation until equilibrium is reached. The timescale for tidal locking depends on several factors: the size of the orbiting body, its distance from the primary, the strength of the tidal forces, and the internal structure of the body being locked. Smaller moons close to their planets lock quickly, in millions of years. Larger moons farther away take longer, hundreds of millions or billions of years. But given enough time, if the orbit is stable and the bodies do not undergo major perturbations, tidal locking is nearly inevitable. The Moon locked to Earth, perhaps 1 billion years after its formation, maybe sooner. We cannot know exactly when the process completed, because the evidence is subtle, and the timescales are vague. But geological studies and modeling suggest that by the time complex life was evolving on Earth, the Moon was already showing the same face. Every creature that has ever looked up at the Moon has seen the same pattern of light and shadow. The constancy we observe is ancient, older than visible life on our planet. And this constancy has had consequences. The Moon's gravitational pull stabilizes Earth's axial tilt, preventing wild swings in the angle at which our planet presents itself to the Sun. This, in turn, stabilizes Earth's climate. The seasons follow a predictable pattern. Ice ages come and go on timescales we can study. Without the Moon, Earth's tilt might wobble chaotically, making long-term climate stability difficult, and perhaps preventing the development of complex life. So the tidal locking of the Moon is not just an interesting curiosity. It is part of the architecture of stability that makes Earth habitable. The same forces that locked the Moon's rotation have helped create a world where change is gradual, where organisms can adapt, where intelligence can evolve and persist. The cosmic handshake between Earth and Moon is, in a very real sense, part of the reason you exist. To ponder it, the agreement reached through tidal forces, the equilibrium achieved over billions of years, has shaped not just the Moon's motion, but the entire environment of our planet. And yet, the handshake is not quite complete. Earth is still slowing still losing rotational energy. To tides. The day lengthens. The moon drifts away. The process continues, patient as ever, toward that distant future, when Earth too will be locked, when both bodies will have settled completely into their minimum energy state, when the dance will be fully synchronized, and the only motion will be the slow orbit around their common center of mass. That future is far away, farther than human civilization, farther than our species may last. But it is there, waiting in the mathematics, inevitable, unless something intervenes to disrupt the system. For now, we have a moon that shows one face, a moon that has completed its half of the agreement, a moon that teaches us, if we are willing to learn, about patience, about equilibrium, about the way all things in the universe eventually find their place of rest. The phrase "dark side of the moon" entered popular consciousness, perhaps most famously through Pink Floyd's album. But the term is misleading. The far side of the moon is not dark. It receives just as much sunlight as the near side during the lunar day, which lasts about 2 Earth weeks. The sun shines on whatever hemisphere faces it, regardless of whether that hemisphere faces Earth or the stars. The correct term is far side. This is the hemisphere we cannot see from Earth's surface, hidden not by shadow, but by the moon's geometry and its locked rotation. It is far from us, perpetually turned away, kept secret by the synchronization between the moon's spin and its orbit. Why can we never see it? The answer is simply tidal locking. Because the moon rotates once per orbit, the same hemisphere is always Earth-facing. There is no rotation independent of the orbital motion. That would eventually bring the far side into view. The moon does not turn away. It cannot. Not without changing its rotation rate, which would require energy the moon no longer has. But the situation is slightly more complex than perfect locking might suggest. The moon's orbit is not a perfect circle. It is an ellipse. This means the moon's orbital speed varies. When closer to Earth, it moves faster. When farther away, it moves slower. But the moon's rotation rate is constant. This creates a slight mismatch between rotation and orbital position, a back and forth wobble we call libration in longitude. There is also libration in latitude, caused by the tilt of the moon's rotational axis relative to its orbital plane. As the moon orbits, we see it sometimes from slightly above and sometimes from slightly below its equator. These librations allow us to peek around the edges of the near side. Over time, we can see about 59% of the moon's surface from Earth. Not just the 50% we would see if the moon were perfectly locked and perfectly circular in its orbit. The remaining 41% remains forever hidden, visible only to spacecraft that have ventured around the moon. The first humans to see the far side were the crew of Apollo 8 in 1968, as their spacecraft swung around the moon, entering lunar orbit. The hidden hemisphere came into view. They described a landscape similar to the near side in its cratered appearance, but noticeably different in detail. Fewer maria, more highlands, a terrain that looked older and less modified by volcanic activity. Why the difference? The explanation likely involves the moon's internal structure and the tidal forces that shaped it. The near side, facing Earth, experienced stronger tidal heating. The crust may have been thinner, allowing molten material to rise more easily and create the dark basaltic plains we call seas. The far side, shielded from Earth's strongest tidal influence, retained a thicker crust that prevented as much volcanic resurfacing. This is speculative, but the correlation is clear. The side that faces Earth is geologically distinct from the side that faces away. Tidal locking has not just oriented the moon, it has shaped its very structure. And now, having mapped the far side, having sent probes and landers to study it, we know that it holds no great mysteries beyond what the near side teaches us. No alien bases, no hidden oceans, no realms where the laws of physics differ. Just more cratered terrain, more ancient rock, more evidence of the same processes that shaped the visible hemisphere. Yet the far side retains a psychological mystique. It is the hidden part, the face turned away, the hemisphere that exists independently of our observation for all of human history until the 1960s. This landscape existed unseen, unknowable except by inference. It reminds us that the universe is full of places beyond our direct perception, that what we see is always incomplete, that there are always other perspectives, other views, other sides to every story. The moon's far side is not dark, but it is secret, in a way the near side can never be. It is the part of the moon that does not belong to Earth, the part that faces the stars, rather than our world. And in that, there is a kind of dignity. The moon is not entirely ours, not entirely defined by its relationship to Earth. It has another face, another identity, hidden from us by the geometry of its orbit and the patient work of tidal forces. This duality, near and far, visible and hidden, is a direct consequence of tidal locking. If the moon rotated independently, we would see all sides eventually. But because it is locked, because it has settled into this particular equilibrium, it maintains a division, half for Earth, half for the cosmos. And we, standing on Earth's surface, see only what the moon chooses to show us. Or rather, what the laws of physics allow us to see. The same face, orbit after orbit, year after year, millennium after millennium, constant, reliable, familiar, but knowing that another face exists, hidden just beyond the limb, unreachable from our perspective, adds depth to the moon's presence. It is a reminder that even the most familiar objects contain mysteries, that what we see is not all there is, that the universe keeps secrets, not out of malice, but simply because the geometry and physics do not allow us to see everything from one vantage point. The far side exists. It always has. And the reason we never see it is the same reason the moon shows us any face at all. Tidal locking. That cosmic agreement between gravity and motion, between Earth and its eternal companion. If tidal locking is a consequence of gravity and time, then we should expect to see it throughout the universe. And we do. Everywhere we look. Wherever a small body orbits close to a larger one, tidal forces are at work, slowly synchronizing rotations, creating the same phenomenon we observe with our moon. Start with Jupiter, the giant of our solar system. Jupiter has dozens of moons, but 4 stand out: Io, Europa, Ganymede, and Callisto, the Galilean satellites. All 4 are large enough to be worlds in their own right, and all 4 are tidally locked to Jupiter. Io, the innermost, is perhaps the most dramatic example. It orbits close to Jupiter, so close that tidal forces are intense. The moon flexes constantly as it orbits, heated internally by tidal friction. This heating is so strong that Io is the most volcanically active body in the solar system. Sulfur volcanoes erupt continuously, resurfacing the moon and giving it a mottled yellow-orange appearance. But despite this activity, or perhaps because of it, Io is locked, one face always toward Jupiter. The tidal forces that heat it also control its rotation. Europa, farther out, is also locked. Beneath its icy surface likely lies a global ocean, kept liquid by tidal heating. The same forces that synchronize its rotation provide the energy that might support life in that dark water. Europa always shows Jupiter the same face, but beneath that face, ocean currents might flow, driven by the warmth of tidal friction. Ganymede and Callisto, larger and farther from Jupiter, are locked as well. They orbit more slowly, experience weaker tides, but the principle is the same. Given enough time, tidal forces have synchronized their rotations. from Jupiter's cloud tops. These moons would appear stationary in orientation, always presenting the same hemisphere. Saturn's moons tell a similar story. Titan, the largest, is locked. So is Enceladus, that small icy world, with geysers erupting from its south pole. Geysers powered partly by tidal heating. Mimas, Rhea, Dion, Tethys, all locked. The pattern repeats itself. Around the ringed planet, moon after moon, showing the same behavior. Even Pluto, demoted from planetary status, but no less interesting, participates in this dance. Pluto and its large moon Charon are mutually tidally locked. Not only does Charon show one face to Pluto, but Pluto shows one face to Charon. They orbit their common center of mass, which lies between them, rather than inside either body, and they rotate in perfect synchrony. If you stood on the Pluto-facing side of Charon, you would see Pluto motionless in the sky. If you stood on the far side, you would never see Pluto at all. The same is true from Pluto's surface. Charon would be visible from one hemisphere and invisible from the other. This is the future of the Earth-Moon system. Billions of years hence. Double tidal locking. Both bodies showing one face to each other, rotating together like partners in an eternal waltz. But tidal locking is not limited to moons. Some exoplanets, planets orbiting other stars, are likely locked as well. The ones we call hot Jupiters orbit very close to their host stars, closer than Mercury orbits the Sun. At such distances, tidal forces are immense. These planets likely became tidally locked early in their history. One hemisphere bakes under constant starlight, reaching temperatures of thousands of degrees. The other hemisphere faces eternal night, cold and dark. Between them, fierce winds transfer heat, creating weather systems of unimaginable scale. Even some smaller planets in our own solar system might be locked to the Sun, though the evidence is less clear. Mercury was once thought to be locked, always showing the same face to the Sun. But we now know it has a 3:2 spin-orbit resonance instead. It rotates 3 times for every 2 orbits. This is still a kind of locking, a different synchronization, another solution to the same gravitational question. Venus rotates so slowly. One Venusian day lasts longer than one Venusian year that some scientists have speculated tidal forces from the Sun played a role in slowing it down. The truth is more complex and less certain, but the principle remains. Tidal forces affect everything. Wherever gravity acts across distance, wherever one body orbits another, tidal locking is a possible outcome. The time it takes to reach tidal lock depends on many factors. Distance is crucial. The closer the orbit, The stronger the tides, the faster the locking. Mass matters too. A small moon orbiting a massive planet will lock quickly. A large planet orbiting a distant star might take billions of years, or might never lock at all. If other perturbations prevent equilibrium, but the trend is clear. Given enough time, given stable orbits, given the patient work of tidal forces, rotation synchronizes. It is not guaranteed. Some systems are too dynamic, too disturbed by other bodies, too young to have reached equilibrium. But it is common, perhaps even typical. This universality tells us something profound. Tidal locking is not a quirk of the Earth-Moon system. It is a fundamental outcome of orbital mechanics and energy dissipation. It is what happens when gravity and time work together on rotating bodies. It is the solution that physics finds to the problem of energy loss in orbit. And everywhere we look, we see this solution being implemented. Moons locked to planets, planets locked to stars, binary systems locked to each other. The universe is full of worlds, showing one face to their companions, rotating in synchrony, settled into the minimum energy configuration that tidal forces allow. Our moon is part of a cosmic pattern. It is not unique in its locking, though it may be unique in the details. Other systems have their own stories, their own histories of how tidal forces shaped them, but the underlying mechanism is the same: gravity, friction, energy loss, equilibrium. In this, there is a kind of elegance. The universe does not create special rules. For each system, the same physics applies everywhere. The same forces work on Jupiter's moons as on exoplanets light years away. The same slow synchronization happens wherever conditions allow. Tidal locking is a universal phenomenon, a testament to the consistency of natural law. And our moon, showing its single face to Earth, is our local example of this cosmic principle, a reminder that we are part of something larger, something that extends far beyond our planet and solar system, a reminder that the patterns we see here echo across the universe, wherever gravity holds sway, and time is patient enough to let equilibrium emerge. There is a clock in the sky, ancient and reliable. It is the moon, marking months with its phases, marking time with its rising and setting. But this clock is slowing, imperceptibly from day to day, unmeasurable across human lifetimes, but relentlessly across the eons. The Earth-Moon system is not static. It appears stable because our perspective is so brief. But zoom out to geological time, and the changes become clear. Earth is slowing its rotation. The moon is drifting away. The day lengthens. The month lengthens. And eventually, though eventually is billions of years from now, both will settle into a final configuration from which neither can escape. Without external intervention, we have already discussed how tidal friction slows Earth's rotation. The moon's gravity pulls on the tidal bulge in Earth's oceans and crust. Because Earth rotates faster than the moon orbits, this bulge is carried ahead of the moon's position. The moon's gravity pulls backward on the bulge, creating a torque that opposes Earth's rotation. Over time, this torque does its work. The spin slows. The effect is small, about 1.7 milliseconds added to the day each century. At this rate, it would take 50,000 years for the day to lengthen by 1 second. But multiply 50,000 years by 1,000, by 1,000,000, and the effect accumulates. 1 billion years ago, an Earth day was roughly 22 hours long. 2 billion years ago, perhaps 20 hours. Go back to the earliest days of the solar system, and a day might have been only 5 or 6 hours. We can see evidence of this in the geological record. Growth patterns in ancient corals show daily and yearly cycles. By counting the number of daily growth rings per yearly cycle, paleontologists can estimate how many days there were in a year at various points in Earth's history. The farther back we go, the more days per year, which means shorter days. The coral record confirms what the physics predicts. Earth has been slowing down. As Earth slows, angular momentum is transferred to the moon. The moon's orbit expands. It moves farther away. Today, laser ranging experiments, bouncing light off reflectors placed on the moon by Apollo astronauts, show that the moon recedes at about 3.8 centimeters per year. This has been going on for billions of years. When the moon first formed, it may have been only 25,000 kilometers from Earth. Now it is 384,000 kilometers away. That is a significant migration. The recession is slowing down. As the moon moves farther away, tidal forces weaken. The rate of angular momentum transfer decreases. Eventually, the recession will slow to nearly nothing. As the system approaches double tidal locking, what will that look like? In the distant future, perhaps 50 billion years from now, if the sun has not already engulfed both Earth and Moon in its red giant phase, the Earth-Moon system will reach equilibrium. Earth's rotation will have slowed to match the Moon's orbital period. The Moon will have receded to a greater distance. Both bodies will be locked to each other. At that point, the day and the month will be the same length, perhaps 50 or 60 current Earth days. One side of Earth will always see the Moon hanging motionless in the sky, growing and shrinking through its phases. but never rising or setting. The other side of Earth will never see the moon, and from the moon's perspective, Earth will be similarly fixed, visible from one hemisphere, but not the other. This is maximum stability. No more tidal friction between Earth and Moon, because the tidal bulges will be aligned with the Earth-Moon line at all times. The system will have reached its minimum energy state. The slowing will stop. The recession will stop. And both worlds will orbit their common center of mass in perfect, eternal synchrony. But there is a caveat. The sun will still raise tides on both Earth and Moon. Solar tides are weaker than lunar tides, but they exist, and they will continue to affect the system, creating new perturbations, new slow changes. The final equilibrium might never truly be reached, or might be reached only to be slowly altered again by the sun's influence. More immediately relevant is the sun's evolution. In about 5 billion years, the sun will begin to swell into a red giant. Its outer layers will expand, possibly reaching Earth's orbit. At that point, questions about tidal locking become moot. The Earth-Moon system will likely be destroyed, vaporized, or at least drastically altered by the dying sun's expansion. So the ultimate equilibrium of double tidal locking may never occur. The timeline of stellar evolution might overtake the timeline of tidal evolution, but the direction of change is clear. If given infinite time, if the sun did not evolve, the Earth-Moon system would settle into mutual locking. This is where tidal friction leads. This is the end point of the process. For now, we live in an intermediate state. The moon is locked to Earth. Earth is not locked to the moon. The system is still evolving, still transferring angular momentum, still slowing down. The changes are too slow to measure in human experience, but they are real. They are happening. Every day is a tiny bit longer than the day before. Every year, the moon is a few centimeters farther away. This slow evolution is written into the structure of time itself. Not time in the abstract sense, but time is measured by rotation and orbit. Time is marked by the clock in the sky. The moon that lit the nights of the dinosaurs was closer, larger in the sky. The Earth that spun beneath them rotated faster, with shorter days. The system was younger, more energetic, less settled. We live in the calm middle period. The moon is tidally locked, providing us with a constant phase. Earth still rotates independently, giving us day and night on a familiar cycle. But the system is winding down, settling, approaching the equilibrium it will never quite reach before the sun's evolution intervenes. In this There is a kind of melancholy. Everything is temporary. Even the celestial dance that has defined our planet for billions of years is changing, heading toward an end state that may never be realized. The moon will drift away. The day will lengthen. The month will lengthen. And eventually, if enough time were granted, both Earth and Moon would face each other in eternal stillness. But for now, the moon rises and sets. The tides flow and ebb. Earth spins, and the stars will overhead. We live in the moment of transition, the long, slow fall toward equilibrium. And the moon, already at rest in its rotation, watches patiently as Earth follows the same path. It took long ago. If you want to understand why the moon is tidally locked, you must understand entropy, not just as a measure of disorder, though it is that, but as the fundamental driver of change in the universe. Entropy is the reason time has an arrow. It is the reason energy flows from hot to cold, from concentrated to dispersed, from organized motion to random heat. And it is the reason the moon's rotation slowed to match its orbit. Entropy is often described as disorder, but this can be misleading. A better way to think of it is as the number of possible states a system can have. A system with high entropy has many possible configurations that look roughly the same at a macroscopic level. A system with low entropy has few such configurations. The second law of thermodynamics tells us that isolated systems evolve toward states of higher entropy. They move from fewer possible configurations to more possible configurations, from special to generic, from organized to random. How does this apply to the moon? Consider rotational energy. When the moon spins, every particle in it is moving in a coordinated way. The motion is organized, directional. There is only one way to have this particular rotation at this particular rate. This is low entropy, high organization. But when tidal friction converts rotational energy into heat, that organized motion becomes disorganized. The energy is no longer all moving in one direction. It is spread out among countless atoms and molecules, vibrating randomly, moving in every direction. There are many ways to distribute this thermal energy. This is high entropy, low organization. The transition from rotation to heat is irreversible because entropy increases. The organized motion does not spontaneously become organized again. The heat does not spontaneously become rotation. Statistically, it could happen. Nothing in physics absolutely forbids it. But the probability is so low as to be effectively zero. It is like dropping a deck of cards and having them land in perfect order. Possible, but so unlikely. You would never see it in the lifetime of the universe. So the moon's rotation slowed because converting rotational energy into heat increases entropy. The universe prefers higher entropy states, not because of any intention or desire, but because there are more ways to be disorganized than organized. The moon wandered, probabilistically, into higher entropy configurations, and tidal friction was the mechanism by which it got there. Tidal locking represents a minimum energy state for the moon's rotation, given its orbit around Earth. It is the configuration where the moon loses the least energy to tidal friction. Any rotation faster or slower than the locked rate would create displaced tidal bulges, which would create friction, which would convert energy to heat and increase entropy. The locked state is where entropy production is minimized. For the rotational degree of freedom, this might seem paradoxical. Does tidal locking decrease entropy by creating order? No. Tidal locking is not a decrease in total entropy. It is a configuration where further increases in entropy are slow or negligible because there is no more rotational energy available to convert. The moon has already given up its excess rotation to entropy. What remains is the minimum rotation compatible with its orbit. Think of it this way: a ball rolling across a floor eventually stops because friction converts its kinetic energy into heat, increasing entropy. The final state, a motionless ball, is not low entropy. It is the state where the kinetic energy has been completely converted to heat. The ball is at rest because there is no more organized motion to dissipate. Similarly, the moon is tidally locked because there is no more independent rotational motion to dissipate. The only rotation remaining is the synchronous rotation, which produces negligible tidal friction because the bulges stay aligned. The moon has reached the end of its entropy journey for this degree of freedom, but entropy is still at work. In the Earth-Moon system, Earth's rotation is still slowing, still losing energy to tidal friction, still increasing the total entropy of the universe. That process will continue until Earth is also locked, or until external factors, like the sun's evolution, intervene. And even beyond the Earth-Moon system, entropy drives everything. Stars burn hydrogen into helium, releasing energy and increasing entropy. Galaxies disperse. Black holes evaporate. The universe expands and cools, moving toward a state of maximum entropy, where all energy is evenly distributed and no work can be done. This is the heat death, the ultimate end point of cosmic evolution. The moon's tidal locking is a tiny, local example of this universal trend. Energy was concentrated in rotation, Tidal friction dispersed it. Entropy increased, and the moon settled into the configuration that allowed the least further increase. There is a beauty in this, a kind of mathematical inevitability. The moon did not choose to lock. It did not decide anything. It simply followed the laws of thermodynamics, moving from lower entropy to higher entropy, from organized motion to dispersed heat, until it reached a state where no more energy could easily be extracted, and in that state, it rests, still rotating, still moving, but rotating at exactly the rate that gravity demands, moving in exactly the way that minimizes energy loss. The moon has found its place in the landscape of entropy, a valley from which it cannot escape without external energy being added to the system. This is true for all tidally locked bodies. Europa, Io, Titan, Charon, the exoplanets around distant stars, all have followed the same path. All have given up their independent rotation to entropy. All have settled into synchronous states, where further energy loss is minimal. Entropy is often associated with decay, with the running down of the universe, with the end of all things. But it is also the reason for stability. Tidal locking is stable because it is the low energy, high entropy state. Perturbations are resisted. The system wants to stay where it is because moving away would require energy that is not available. So the moon's locked rotation is not a failure or a loss. It is an achievement of sorts. It is the state the moon was always heading toward, the destination written into the mathematics from the moment it formed. And now that it has arrived, it can remain there, stable and constant, for as long as the laws of physics allow. Entropy drives change, but it also creates equilibrium. It pushes systems towards certain states and then holds them there. The moon is proof of this. It is a world that has completed its journey, at least in terms of rotation. It has given all it can give to entropy, and what remains is the synchronized spin that we observe from Earth. In this, the moon teaches us about the deep structure of reality, not just the mechanics of orbits and gravity, but the thermodynamic arrow that underlies all change. Everything tends toward higher entropy. Everything moves from order to disorder, from motion to stillness. And the final stillness is not death, but equilibrium, a state where no more change is easily possible, a state of rest. The moon rests in its locked rotation, And in that rest, it shows us the destination of all things, not chaos, but balance. Imagine a future Earth, billions of years from now. The sun is older, perhaps slightly larger, though not yet the bloated red giant it will eventually become. The sky is different, bluer perhaps, or hazier. The continents have shifted, unrecognizable from any map you know. And in that sky, the moon hangs, but it does not move. Not in the way we mean today. It does not rise or set. It does not climb above the horizon in the evening, or sink below it at dawn. It simply hangs there, in one position, fixed relative to the ground beneath you. From this hemisphere of Earth, the moon-facing hemisphere, the moon is always visible. It goes through its phases as the sun's angle changes, waxing and waning, from new to full, and back again. But its position in the sky never shifts. It is a permanent resident, a feature as fixed as a mountain. If you walk far enough, thousands of kilometers perhaps, you will eventually reach the terminator, the line that divides the moon-facing hemisphere from the opposite side. Cross that line, and the moon sinks below the horizon. Walk farther, and it disappears entirely. On the far side of Earth, the hemisphere that faces away from the moon, the sky is empty of our satellite. No moon rises. No moon sets. It is simply absent, always below the horizon, hidden by Earth's bulk. This is double tidal locking. Earth's rotation has finally slowed to match the moon's orbital period. The day is perhaps 50 Earth days long. Maybe 60, perhaps even more. For half of that long day, the sun shines. For half, darkness. But the moon's position remains constant, visible from one hemisphere, invisible from the other. What would life be like on such an Earth? Assuming life still exists, assuming the long day and the changed climate allow for biology, the experience of time would be profoundly different. The familiar 24-hour rhythm would be gone. Instead, weeks of sunlight, followed by weeks of darkness. Organisms would need to adapt to this new cadence, or they would perish. The tides would be different too. With Earth locked to the moon, the same regions would always experience the strongest lunar pull. There would be equilibrium tides, persistent bulges, rather than the twice-daily rise and fall we know today. Currents might still flow, driven by the sun or by temperature differences, but the old rhythm of the oceans would be gone. From the moon's perspective, Earth would be fixed as well. One hemisphere of the moon would always see Earth, large and blue, cycling through its phases. The other hemisphere would see only stars. The division would be permanent, unchanging. This is the ultimate fate of the Earth-Moon system. Barring external disruption, this is where tidal friction leads to mutual locking, where both bodies show one face to each other, where rotation and revolution are perfectly synchronized, where the energy of independent motion has been dissipated into heat and radiated away. But will this future ever arrive? Probably not. The sun's evolution will likely intervene first. In about 5 billion years, the sun will swell into a red giant. Its luminosity will rise. Its outer layers will expand. The inner planets, Mercury, Venus, possibly Earth, will be transformed, perhaps engulfed, perhaps stripped bare. Even if Earth survives, oceans may boil away. The atmosphere may thin. The surface may become unrecognizable. The moon, too, will feel the sun's change, though it is more resilient in its airless stillness. So the double-locked future is likely a destination the mathematics points toward, but stellar evolution prevents. An asymptote, approached but never reached. Still, contemplating this future matters. It reveals the direction of change. It shows the stability tidal locking represents. It reminds us that our present configuration, moon-locked, Earth spinning freely, is temporary. We live in a transitional era, billions of years long, yet brief on cosmic scales. The moon we see rising and setting is not the moon of the far future. That moon will be more distant, smaller in the sky, fixed for half the planet. The Earth beneath it, slower, stranger, a world with days longer than any month we know. And yet, the mechanism remains the same. Tidal forces, working patiently, dissipating energy, moving the system toward equilibrium. The moon has arrived. Earth is on its way. Given infinite time, they would meet in that final configuration, locked together in a dance that no longer changes. It is a quiet future, not violent, not dramatic, just still. A stillness born of entropy, of energy dispersed, of gravity's patient work. A future where the moon does not rise, because it no longer needs to. It is already where it belongs. The moon is more than a light in the sky. It is more than a subject for poetry, or a target for exploration. It is a stabilizing force, a geological partner, a reason that Earth is the kind of world that can support complex life. Consider the tilt of Earth's axis. Earth is tilted about 23.5 degrees relative to the plane of its orbit. This tilt creates the seasons. When the northern hemisphere tilts toward the sun, summer. When it tilts away, winter. A regular rhythm that life has adapted to over millions of years. But the tilt is not perfectly fixed. It wobbles, slowly, predictably, changing by small amounts, over thousands of years. Without the moon, that wobble would not remain small. The tilt could vary wildly, swinging toward extremes, bringing chaotic climate shifts, making long-term stability difficult. The moon stabilizes Earth's tilt. Its gravity pulls on Earth's equatorial bulge, acting like a gyroscope, resisting large changes, keeping variations small, keeping seasons predictable, giving ecosystems time to adapt. Mars shows the contrast. With no large moon, its axial tilt swings dramatically over millions of years, creating severe climate shifts. Earth, by comparison, remains steady. The moon keeps the range narrow, keeps the climate from veering into chaos. The moon also shapes Earth's rotation. Tidal friction slows the spin, lengthening the day, moderating extremes. In the early solar system, the moon's influence began immediately, helping regulate Earth's rotation, preventing it from remaining too fast or becoming unstable. And then there are the tides, the daily rise and fall of the oceans, mixing nutrients, feeding coastal ecosystems, driving currents, redistributing heat, shaping coastlines. In the distant past, tidal pools may have helped life emerge, concentrating chemistry, creating cycles of wet and dry. The moon is not decoration. It is participation. It is influence, woven into Earth's geology, into its climate, into its biology. And the moon is locked, stable, predictable, unchanging in orientation. Its gravitational pull, consistent, reliable, always acting in the same way. Imagine if it were not locked. If it tumbled unpredictably, the tides would vary. The stabilizing effect would weaken. The system would grow more chaotic, less reliable. But it does not tumble. It settled into equilibrium. Billions of years ago, it presents the same face, again and again, century after century, epoch after epoch. In that constancy, there is structure, there is partnership. Tidal locking is not a trivial detail. It is part of the architecture of Earth's habitability. When we search for distant worlds, we might ask, do they have moons large enough to steady their tilt, to calm their climates, to provide the quiet gravitational discipline that stability requires? The moon's story, its formation, its locking, its influence, is intertwined with ours. We are not separate from it. We are part of a system, co-evolving for billions of years. The moon shapes Earth. Earth shapes the moon. And the result is this world, with its seasons, its tides, its steady rhythms. Tidal locking is not a footnote. It is fundamental to why Earth is the way it is. When you look at the moon and see the same craters, the same Maria, the same familiar face, you are seeing stability, predictability, a gravitational partnership that made this world possible. The moon's constant phase is not intention, not design, but consequence, a consequence of physics that happens to benefit us. And in that consequence, there is a quiet kind of grace. There is something deeply reassuring about the moon's unchanging face. In a world of flux, where everything shifts, changes, and eventually fades, the moon remains. The same features, the same light, the same quiet presence. Human beings crave consistency. We build routines, traditions, rituals. We return to familiar places. We seek patterns we can rely on. And the moon, perhaps more than any other celestial object, provides that constancy. Every culture has looked up and seen the same moon. Ancient Egyptians, Babylonians, Chinese dynasties, Mayan astronomers, all saw what we see. The same near side, the same Maria, the same bright rays, spreading from younger craters. The moon has been a constant companion to every civilization, every empire, every human who has ever lived. This constancy is not accidental. It is the result of tidal locking, of billions of years, of synchronization, of gravity, energy, entropy. The moon's unchanging face is written into the structure of the universe. But why does this matter to us? Emotionally, psychologically, spiritually. Perhaps because the moon represents something beyond us. It was here before us. It will remain after us. It is ancient, in a way civilizations cannot be. When we look at it, we connect to something timeless, something that transcends the brief flicker of our lives. The moon has witnessed everything, every war, every peace, every birth, every death. It shone on the first humans, on the African savanna. It lit the nights of dinosaurs. It watched when life was only single cells. In ancient oceans, and long after we are gone, it will still orbit, still locked, still showing the same face. This continuity is profound. It gives us a sense of place and time. We are part of a larger story, one that began long before us, and will continue long after. The moon stands as witness, unchanging, while everything else transforms. There is honesty in its locked rotation. It does not turn away. It always faces us, even when it is new, invisible in sunlight. We know it is there. We know exactly what face it would show if we could see it. This predictability is comforting. The moon rises and sets on a schedule we can calculate. Its phases unfold with quiet precision. There are no surprises. The moon is reliable in a way few things are. And yet, it is not frozen. It orbits. It waxes and wanes. It participates in eclipses. It moves, but its face remains. This balance, motion and constancy, change and permanence, is what makes it compelling, familiar, yet never dull, predictable, yet always worth looking at. Cultures project meanings onto it. A face, a rabbit, figures and myths. Interpretations differ, but the patterns are shared. The moon is universal because it is universally constant. In an age of rapid change, when technology reshapes life, when information overwhelms, when the future feels uncertain, the moon is an anchor. The same moon that guided our ancestors will guide those yet to come. A bridge between past and future. There is also a quiet lesson in tidal locking. The moon did not resist. It did not fight the forces acting on it. It moved toward equilibrium, settled into balance, and in that settling, found stillness, not death, but equilibrium. Perhaps there is wisdom there. In a life of struggle, there may be value in aligning with deeper patterns, with larger forces, with the structure of reality itself. The most stable state may not be forced, but allowed to emerge. Of course, the moon is not conscious. It did not choose. It is rock, following gravity. Nothing more. But the meaning we find in it is real to us. The comfort is real. The connection across generations is real. The moon becomes a mirror, reflecting our need for stability, for continuity, for something enduring. Its locked rotation reminds us that constancy is possible, that equilibrium, once reached, can last for billions of years, that the same face can shine on generation after generation after generation. This is the gift of tidal locking, not merely orbital mechanics, but reassurance, a reminder that we belong to something ancient, something enduring, a light in the darkness that does not flicker and does not fade. There is a kind of beauty in things that move together, in flocking birds that turn as one, in schools of fish that flow like liquid, in dancers who match their steps to music. Synchronization creates harmony, a sense that individual parts are working together toward a common pattern. The moon's tidal locking is synchronization at a cosmic scale. It is the moon matching its rotation to its orbit, moving in perfect harmony with the gravitational pull of Earth. One rotation per orbit. No deviation. No drift. Perfect timing, maintained across billions of years. This is not synchronization imposed from outside. There is no conductor, no choreographer. The synchronization emerges naturally from the interaction of gravity and motion. The moon finds its rhythm through the patient work of tidal forces, settling into the configuration that is stable, sustainable, minimal in energy loss. In this, there is an elegance. The universe does not need external guidance to create order. Order emerges from the laws of physics themselves. Tidal locking is not designed or planned. It is a consequence, an outcome, a pattern that arises when gravity acts on rotation over time. And this pattern is not unique to the moon. We see synchronization throughout the cosmos. Moons orbiting planets, all showing the same face. Binary stars orbiting each other, their rotations synchronized. Even at smaller scales, atoms in crystals, electrons in superconductors, neurons firing in the brain, we find synchronization. It is a universal principle, a way that individual components can move together to create something larger than themselves. Why does synchronization happen so readily? Because it is often the lowest energy state. When components move out of sync, they create friction, resistance, turbulence. When they move in sync, they minimize these losses. Synchronization is efficient. It is stable. It is the natural endpoint of many dynamic systems. The moon's locked rotation is an example of this principle. The locked state minimizes tidal friction. It allows the moon to orbit with the least internal stress, the least energy dissipation. It is the solution that physics finds to the problem of how to maintain an orbit while losing the minimum amount of energy. And there is a beauty in this solution. Not beauty in the aesthetic sense, though the moon is certainly beautiful to look at, but beauty in the mathematical sense. Elegance, simplicity, a complex problem resolved into a simple, stable configuration. Think of the geometry. The moon's long axis always points toward Earth. The tidal bulges align with the Earth-Moon line. The rotation rate matches the orbital rate. Everything fits together. There is no wasted motion, no unnecessary complexity. Just a clean, harmonious relationship between rotation and revolution. This is the beauty of natural law. The universe creates patterns without trying. It finds solutions without searching. It moves toward equilibrium without intention. And the result is a kind of order that is both simple and profound. From our perspective on Earth, This synchronization gives us the gift of the moon's constant phase. We see the same features, the same patterns, the same landscape. This constancy is reassuring, familiar, grounding, but it is also beautiful in its own right. The fact that the moon shows us one face is not arbitrary. It is a consequence of deep physical principles, of the way gravity and time interact, of the path toward equilibrium. And the beauty extends beyond just the moon. The entire Earth-Moon system is moving toward a synchronized state. Earth's rotation is slowing, approaching the point where it too will match the moon's orbital period. The system is finding its collective rhythm, moving toward double tidal locking, toward the configuration where both bodies are in perfect sync. This future state, if it is ever reached, will be even more synchronized than the present. Both bodies locked to each other, rotating together, orbiting their common center of mass, like two dancers holding each other and spinning, one face to the other, forever. Perfect mutual synchronization. There is something profound in this image. Two worlds, moving together through space, always facing each other, locked in a gravitational embrace that nothing can break. It is not romantic in the human sense. These are balls of rock and metal, not conscious beings. But there is a kind of cosmic poetry in it nonetheless. Synchronization is also a theme in human life. We synchronize our steps when we walk together. We synchronize our breathing when we meditate. We synchronize our clocks to coordinate our activities. We synchronize our movements in sports, in music, in work. Synchronization allows us to act as groups, to create patterns larger than any individual could create alone. And perhaps, in looking at the moon's tidal locking, we see a reflection of this human need for harmony. We see a universe that, at every scale, tends towards synchronized motion when conditions allow. We see that moving together, matching rhythms, finding common beats, is not just a human preference, but a cosmic principle. The moon teaches us that synchronization is not forced or artificial. It is natural. It emerges from the fundamental laws that govern motion and energy. It is what happens when systems are allowed to evolve toward their stable states. And there is beauty in that. Beauty in the fact that the universe, left to its own devices, creates patterns, creates harmony, creates moments of perfect synchronization, where everything moves together, where individual motions combine into collective grace. The moon's locked rotation is one such moment. A single world, rotating in perfect time with its orbit, moving through space in a way that is stable, sustainable, beautiful, not designed, but discovered, not imposed, but emergent, a natural consequence of gravity and time, working together to create something that is more than the sum of its parts. When you look at the moon, you are seeing synchronized motion. You are seeing one rotation per orbit, maintained across eons. You are seeing the universe doing what it does best, finding patterns, creating order, moving towards states of harmony and balance. And in that, there is a quiet beauty, the beauty of natural law, written in the motion of worlds. We return to the rooftop, the hillside, the quiet place where you lie back and look up. The stars are there, scattered across the dark, and among them, hanging in that familiar position, is the moon. You understand now what you are seeing, not a frozen object, locked in place by some mysterious force, but a world in motion, rotating, slowly, patiently, once per orbit, showing you the same face, not because it refuses to turn, but because it has found the one rotation rate that is stable, that is sustainable, that allows it to exist in equilibrium with the force that shapes it. The moon does not fight gravity. It dances with it. It moves in rhythm with Earth's pull, synchronized perfectly, locked not by rigidity, but by balance. The tidal forces that once slowed its rotation now maintain it, keeping the same face forever earthward, not through constraint, but through harmony. This is the lesson of the moon. That stillness can be motion. That constancy can be change. That what appears frozen is actually moving at exactly the right speed to maintain its position. The moon is not static. It is dynamically stable, held in place by the same forces that move it. And this lesson extends beyond the moon. It teaches us about time itself, about how everything in the universe eventually finds its rhythm, its equilibrium, its place of rest. The moon found its rhythm billions of years ago, and it has been following that rhythm ever since. Patiently, inexorably, without deviation. Time, for the moon, is measured differently than it is for us. We count hours, days, years. The moon counts orbits. One rotation, one orbit. A month for us is a day for the moon. Time passes at different rates depending on perspective, but the underlying rhythm is the same. Motion, orbit, rotation, the slow dance of gravity and mass. The moon has taught humanity about time. Since before we could write, we measured months by its phases. We predicted tides by its position. We navigated by its light. The moon was our first calendar, our first clock, our first guide to the patterns of the cosmos. And now we understand why that clock is so reliable. Because the moon is locked. Because its rotation matches its orbit. Because it has settled into a configuration that is stable across billions of years. The moon is constant, not by accident, but by physics. In this constancy, there is comfort, but there is also wisdom. The moon teaches us that equilibrium is achievable, that chaos can settle into order, that the wild, violent early solar system with its rapid spins and close orbits could evolve into the calm, stable system we observe today. The moon is proof that time heals, that systems find balance, That entropy leads not to disorder but to peace. We live in a universe that is winding down. Stars are burning out. Galaxies are dispersing. The universe is expanding, cooling, moving toward a state of maximum entropy where all energy is evenly distributed and nothing can change. This is sometimes called heat death. And it sounds bleak. But the moon suggests a different perspective. The moon has reached its heat death. In a sense, it has lost its independent rotation, given up its energy to entropy, settled into its final state. And that state is not death. It is stability. It is balance. It is the configuration that allows the moon to exist, unchanged, for eons. Perhaps the heat death of the universe will be similar. Not an ending, but a settling, a final equilibrium where everything is in balance, where no more energy can be extracted, where change ceases not because nothing can move, but because everything is moving exactly as it should to maintain stability. The moon, locked in its rotation, is a preview of that final state. And it is not frightening. It is peaceful. It is the same moon that has lit our nights for all of human history. It is reliable, constant, beautiful. It is not dead. It is at rest. So when you look at the moon, see more than a satellite. See a teacher, a guide to the deep patterns of the cosmos, a reminder that motion and stillness are not opposites, but partners, a demonstration that time, gravity, and entropy work together to create stability. The moon does not refuse to spin. It has simply found a rhythm that is perfect for its situation. Locked in motion, frozen in time, yet always moving. One rotation per orbit, perfectly synchronized. A dance that has been going on for billions of years, and will continue for billions more. This is the moon's gift to us. Not just light in the darkness, not just a source of tides and stability for Earth's climate, but a lesson in patience, in equilibrium, in the way all things eventually find their place. The moon is patient. It does not rush. It rotates once per month, slow and steady, never deviating. It has all the time in the world, and it uses that time to maintain its balance, its harmony, its synchronized motion. We could learn from this. In a world that demands speed, constant change, perpetual growth, the moon offers a different model. Find your rhythm. Match your motion to your environment. Settle into the configuration that is sustainable, that minimizes friction, that allows you to exist in balance with the forces around you. This is not passivity. The moon is not passive. It is actively rotating, actively orbiting, actively maintaining its locked state through the constant interaction with Earth's gravity. But it is not fighting. It is working with the forces, not against them. It has found the path of least resistance and follows it. And in following that path, the moon has achieved something remarkable. It has maintained the same orientation for longer than life has existed on Earth. It has been constant while continents drifted, while species evolved and went extinct, while everything on Earth's surface changed and changed again. The moon endures because it is in equilibrium. This is the deepest lesson. Equilibrium is not stagnation. It is not the absence of motion. It is motion at exactly the right rate to maintain stability. It is the balance between forces, the harmony between rotation and orbit, the synchronization of individual motion with the larger pattern. Look at the moon. See it not as locked, but as liberated. Liberated from the chaos of independent rotation, liberated into a state of synchronized grace, liberated to be constant in a universe of change. The moon that never turns is the moon that has found its turning. The moon that appears still is the moon that moves with perfect precision. The moon that shows one face has simply learned to face the right direction. This is not a limitation. It is an achievement. And as you lie there, on that rooftop or hillside, watching the moon hang in the sky, you realize something. The moon is not separate from you. You are part of the same universe, subject to the same laws, moving through the same space and time. The forces that locked the moon are the forces that shape your life. Gravity, energy, entropy, time. You too are finding your equilibrium. You too are settling into patterns, into rhythms, into ways of moving through the world that work for you. You too are being shaped by forces larger than yourself. Forces that are patient, inexorable, impossible to resist. But like the moon, you do not need to resist. You can find your rhythm. You can synchronize your motion with your environment. You can settle into the configuration that is sustainable, that minimizes friction, that allows you to exist in balance. The moon teaches us that this is not defeat. It is wisdom. It is the path toward stability, toward constancy, toward the kind of enduring presence that lasts not just for years or decades, but for eons. The moon does not refuse to spin. It has simply found a rhythm, locked in motion, frozen in time, yet always moving forward, orbit after orbit, rotation after rotation, perfectly synchronized with the force that shapes it. This is the moon's story, and in telling it, we have told a story about time itself, about how chaos becomes order, about how motion becomes stillness, about how everything, given enough time, finds its place. The moon has found its place, locked to Earth, showing one face, rotating in perfect harmony with its orbit. And in that place, it rests, not dead, not frozen, but balanced, at peace. When you look at the moon tonight, remember this. You are not seeing an object that has stopped moving. You are seeing an object that has learned to move in exactly the right way. An object that has found its rhythm. and follows it with perfect precision. The moon does not refuse to turn. It has simply learned when to turn, how to turn, at what rate to turn to maintain its eternal presence in our sky. This is the moon's gift. This is its lesson. Locked in motion, frozen in time, yet always moving. The same face, the same light, the same patient teacher in the night sky, showing us what equilibrium looks like when it is achieved across billions of years. Look up, see the moon, and understand what appears still is actually the slowest, most patient dance in the solar system, a waltz between worlds that has been going on since before there were eyes to witness it, and will continue long after those eyes have closed. The moon does not refuse to spin. It has found a rhythm, and in that rhythm, we can read the deepest truths about motion, about time, about the way all things eventually come to rest in the arms of gravity. This is the moon, teacher of time, keeper of constancy, the one face that has watched over Earth for billions of years. And it is still watching, still rotating, still moving in perfect harmony with the planet it orbits, forever facing home.